Yes, I'm presenting my bachelor thesis, which is about LLHD simulation using MLIR. And the objective of the thesis were to implement an LLHD dialect in MLIR together with Martin, and then to actually use that dialect to implement an LLHD simulator. And as a sneak peek of my achievements with this thesis, I managed to implement a working sequential simulator, which seems to be quite robust in regards to correctness and also with a relatively good performance. And also this project, both the dialect and the simulator have already become part of the CIRC project, which is an LLVM incubator project aiming at building a new and open source workflow for hardware design using MLIR. So, but what actually is LLHD? And LLHD is a single static assignment language, which is heavily inspired by the LLVM IR, but is specifically designed to represent hardware rather than software like conventional IRs. So as we also expect from an IR, it contains a fairly small instruction set, which is also quite simple, but it is still powerful enough to fully represent existing hardware description languages such as System Verilog across the entire hardware design workflow. MLIR, on the other side, is this new approach at building compilers by providing a centralized and quite powerful infrastructure, which exposes a multi-level SSA IR, which is then structured in dialects, and it can be freely expanded just by defining new dialects and without requiring to re-implement the whole infrastructure every time. So this can pretty much fit LLHD quite well, we think, and so this was our first step to just implement dialect for LLHD. As for why we then want to build an actual simulator using this representation, so first of all, generally speaking, simulation is quite an important tool in hardware design since it allows us to verify that a design meets its functional expectations by feeding it some input values and then observing if the output values are what we expect without actually requiring us to manufacture the design, which would be quite expensive just for a debugging run. Also looking at the open source theme for System Verilog Simulator, we don't really have a lot of support for the non-synthesizable parts of the System Verilog standard, where meaning that open source simulators have quite an hard time to be competitive against the well-established and proprietary simulators. More specific to our case, being able to correctly simulate our LLHD dialect allows us to assert that it is actually correct and also that LLHD is fully representable in MLIR. And furthermore, it also allows us to assert that whenever we add a new pass to LLHD, that this is correct and it does not change the actual semantics of the design just by comparing the simulation results before and after the pass is applied. And finally, it allows us to just use our LLHD representation, our MLIR representation, rather than having us to implement some way back to the original LLHD representation. And there are a couple of good reasons for that. So first of all, in the long term, the grand plan would be to eventually fully replace the original representation with a new MLIR representation. So in the long term, we don't really need a way back. And also in the short term, the only reason we would want to go back would be to use the existing simulators. But since those are more some quite early research prototypes, I really think we are just better off building a new simulator from the ground up which of course builds on the knowledge of those first implementation, but then also tries to expand on them. So that said, we can now dive in what we actually need to build a simulator. And the first thing that we need is an actual simulation engine. And for that, we are currently using a very simple sequential event-driven approach, where generally in an event-driven approach, we just look at our input design as a collection of processes. And those processes will then be completely isolated from each other and are allowed to only communicate by exchanging and reacting to timestamped events. So what this means in LLHD is that processes will pretty much correspond to LLHD instances, which in turn will be an instantiation of either an LLHD entity, which provides a structural description, or an LLHD process, which provides a structural description of our circuit. The timestamped events will then correspond to just timestamped signal updates. And signals in LLHD are used to represent physical wires which carry some value of some other type. So just to have an intuition, we could pretty much look at them as just conventional pointers to memory location, but with the difference that updating a signal takes some predefined time delay rather than just happening instantly, such as happens with a pointer. So then we also have to consider how can we guarantee the correctness of our approach. And what pretty much happens is that for each simulation cycle, we may get a bunch of new events, and those can arrive in any arbitrary order. But between different events, there may be some dependencies. So for example, here, the 2 nanosecond event will just increase the current signal value by 1, meaning that it will depend on the previous event that updated that exact same signal. So we have a dependency going in this direction. But what can never happen is a dependency in the other direction, because we can just not depend on something that will happen in the future and we don't know nothing about yet. So with that, if we, for example, process our events just in the order of arrival, we may incur in such dependencies that we are not able to fulfill, which can lead to an incorrect simulation. Whereas the simplest thing that we can do is just to process the events in an increasing timestamp order. So this way we can always guarantee that all the dependencies are fulfilled without requiring us to do any kind of dependency analysis between the events. So with all that, we can now build our actual simulation engine by constructing a centralized queue of events where we store all the events that still need to be processed, and where we can also stack together all the events with the same timestamp to avoid some redundancy when processing them. And once we have that queue, we can just pretty much loop over it, always picking the earliest stack of events that we have available, processing all the signal updates that it contains, and determining what instances have to react to those changes. So we can wake them up and finally add to the queue any new events that waking up those instances may have generated. But waking up the instances actually require us to have some means to be able to emulate or execute the underlying LLHD logic that is contained in the instance. And to do that, what we can do is to just take our input LLHD module and convert that to the LLVM dialect that we have in MLIR. And once we have that fully converted module, we can just feed it to the MLIR execution engine, which we have, which is the MLIR JIT compiler. So once we have the fully converted LLVM dialect module, everything else pretty much comes for free with our infrastructure. And the only thing that we really have to care about and to implement is this conversion here. And for that, the first thing that we have to consider is how do we lower the instances. And as I mentioned, instances are an instantiation of some base LLHD unit. But the only real things that change between different instances of the same unit is, of course, the respective local state and also what signals we have connected here as input or output ports. So rather than, for example, compiling all instances independently, what we can do is just to compile the base entity, base units to LLVM functions. And here, and those with generalized signatures such that running different instances of this unit just boils down to passing the correct signal table and local state. Once we have that, we can then move on to compile the actual bodies of the units. And here, of course, we have some quite simple conversions, which include like constants that just can become constants, arithmetic or bitwise operation that have equivalents in LLVM dialect can just be converted one-to-one. And otherwise, we can usually replicate the semantics quite easily, just like a negation that is just a multiplication by -1. But then we also have some more involved examples, and those usually involve working with signals. So for example, here we have a reg operation, and what a reg operation does is pretty much to conditionally update a signal given a list of tuples, each containing a condition and what arguments to update this signal with. So to compile this, the first thing that we can have a look at is what is the end result. And at the end of the day, this operation will always just be a signal update. So what we can do is just to generate a new block in MLIR. And this block will then contain the actual normal LLHD signal update, which is an LLHD drive. But the arguments to this drive, rather than being statically defined, will come from the block arguments. So we can dynamically branch to this block with the arguments that fulfill one of the condition of the tuples. So then we have to have a look at the triggers. So we will always have a trigger and a condition this trigger will has to fulfill. But some of those conditions require us to actually know about more than one state of this trigger. So for example, here that we are looking at a falling edge condition, we cannot determine that with only the current value of the trigger, but we actually need to know what was its value in a previous execution, or else we cannot distinguish that from just a low state, for example. So to do that, what we can do is to just store all of those triggers that have similar conditions in the local state of the instance. And the first thing that we do before actually doing any condition checking is to retrieve those from the local state, load them, and we can also already update that local state with the current value so it is ready for the next execution. The same, of course, we do with all of the other tuples that have similar conditions before actually doing the condition checks. And here we can just generate one block for each condition so that we check the condition and then conditionally drive either to the driving block if the condition is fulfilled or to the next block if not. And finally, if none of the condition is fulfilled, the last block will just completely skip the drive and move on with the remainder of the body. So finally, we need also some kind of output for our simulation. And this is usually in the form of some long list of signal updates, of all the signal updates that happened throughout the entire simulation. And for that, we are currently using this custom textual representation rather than a standard format such as VCD, which provides us with the complete information about the simulation, meaning that we generate trace entries for each of the instances a signal is connected to with the respective full hierarchical path. So we keep track of the entire hierarchy of the design, but also that we maintain the full timestamps that we use in LLHD, which include those delta steps, which represent infinitesimal time steps within a real time step, and epsilon steps, which define absolute slots within a delta step. We also define a complete order over this queue by, of course, having a primary order over the timestamps, but then within one timestamp, we also have a lexicographical order over the hierarchical paths, giving us a nice and well-defined order. So this gives us the benefits of having quite a portable trace, since we can just store that in a TXT file, and thus we can open it with any editor that we want without actually requiring us to have some specific software. A bit on the same note, it is also quite easy to compare, since once again, this is just a TXT file. And then also because we have that well-defined order, we can just have an automated comparison by feeding two traces to any diff checker that we have available. And finally, it is also quite easy to implement, since we can just dump all the information that we want as strings, and we do not need to do any kind of encoding. The main downside, though, is that this is not a standard format, so we don't have a direct means to perform any direct comparison against traces from other simulators. But to address that, I played around with a couple of variations of this format, finally ending up in this format that can actually be compared against VCD. So what we do here is, first of all, we trace only the top level signals of the design. And the reason for that is just that we currently cannot retrieve the original port names for the units in our LLHD dialect. So doing a comparison below the top level would be quite hard, just because we don't have those original names. But still, we can have a good indication of the correctness of the simulation if we consider our underlying circuit as just a black box and only observe its output values, since the correctness of those output values depend on the correctness of the circuit itself. Next, we have to get rid of those delta and epsilon steps, because we don't have them in a VCD trace. And we do that just by squashing together all the time substeps into the respective real time step, ending up with only the final state for each of the signal that had changes in that time step. Finally, we have to get rid of what I call helper signals. And those are signals that are not part of the original design, but are introduced by the LLHD frontend. So they will never have a meaningful name, but rather be only assigned an SSA ID, such as all of those signals here. So they are quite easy to find and to get rid of, leaving us with the exact same information that would be present in a VCD trace. Meaning that we can also translate VCD to this format, and that, for example, just with a fairly simple Python script. Which leads us directly to correctness. So to test for correctness, of course, during development, I defined a bunch of unit tests to make sure that the semantics of the single operations are respected. But then I also took the test set from the LLHD paper and compared the full traces I could generate against the traces generated by Vivado. Once again, since we have this textual representation, this can be automated quite easily just with a bash script and using the command line diff tool. So our results are that we can generate equivalent traces for all of the examples, but not completely matching one. And the reason for that is that we currently don't have logic types being used in LLHD. So the LLHD frontend does not generate logic types, and we also did not implement them in our dialect yet. So whenever he logic typed wire, for example, takes I don't care value in the system Verilog simulation, we cannot represent that in LLHD, and those signals will have an actual integer value instead, which also leads to cases like this one where updating from I don't care value may not be represented in our LLHD trace if that signal is already on that exact same value, because we do not generate a trace entry if there is no actual update for the signal. But still, we can accept those discrepancies if we consider that we are actually simulating slightly different models due to the lack of these logic types, and also considering then that the remainder of the traces otherwise completely match. As for the performance of the simulator, here we have the median runtime values over 10 runs that I measured for my simulator, the two LLHD simulator, as well as Vivado. And as we can see, we have an average runtime being around 2 times lower than the two faster references, which I think is quite impressive, since if we consider that this is only a first implementation on my side that was mainly focused on correctness, and that I had time to implement only a small set of performance considerations. But what I think is actually more interesting than just looking at a performance chart is to look what is actually happening in the simulation and where we're spending time. So if we look at this flame graph generated by running one of the examples, we can see that we have a pretty even split between the time spent in the simulation engine, processing the events mainly, and the time spent in executing units. But zooming in the side of the unit execution, we see that only a small part of that is actually spent executing our lower rate LLHD code, whereas most of the time is spent in the runtime library to spawn new events and to interface with the simulation engine. Also quite interesting is that we do not have entries in this frame graph for the MLIR infrastructure, which means that lowering LLHD to the LLVM dialect and JIT compiling it pretty much has no costs at all for performance in our case. Also, we can see that we have some quite obvious outliers still present in my implementation, such as the AP-int library that I'm using just as a very convenient library to work with arbitrary precision integers when updating signals, and also sorting that I'm using to just make my life easier when processing the different signal updates, just to make sure that all the updates to the same signals are close to each other so that I can pretty much process one signal at a time, making it easier to define whether this is an actual update or not. So to conclude, what we have is a working simulator which is able to simulate a bunch of real-world examples, including a full snitch processor core, and that with a performance that is relatively close with that of LLHD Blaze and Vivado. and that only with a sequential implementation and only a minimal set of performance optimization I had time to implement, which makes, I think, this simulator quite a good optimization target, since, as we have seen, we don't really have any impact that is given by the MLIR infrastructure. So all we have to focus to improve our performance is just the simulation engine. And we still have some quite obvious outliers, which will probably be some really low hanging fruits to improve performance, meaning that there is still some potential to be taken out from the current implementation, but then also by switching to a more advanced algorithm, for example, instead of this sequential approach, I really think we could get some major performance gains. So this would be it from my side, and thank you everyone for listening.